This video I will explain to you in a step-by-step guide using an example how you can compute the unknown currents in a network with the help of the formal branch current method, a method of network analysis. You will learn how to transform a system of node and mesh equations into a linear system of equations from which you can then determine the quantities you are looking for very easily. And although the branch current method is less relevant in practice than other methods such as the node potential method, it's very easy to use and you can learn a lot about networks and setting up equations from it. Now let's talk about the motivation behind this video. Firstly, the determination of currents and voltages in a network is one of the fundamental tasks which you need to perform in electrical engineering, and it ensures the proper operation of components if you have carefully adjusted both voltage and current distributions in your network. Also, a variety of methods exist for this purpose with different advantages and disadvantages and also areas of applications. And an honest note, an honest remark to you, not all methods for network computation are relevant in practice. For example, the branch current method, as I talked about before, it's not used as often. Nevertheless, it's important to deal with them as they really promote the understanding of circuits. The branch current method gives you a deep view in terms of understanding the distribution of all these properties in a network, even though it might not be used as often as, for example, the mesh current method. But now let's start with this branch current method, both in terms of talking about the theory and also making an example in a network, which we will discuss in this video here. Now, overview, the branch current method is one of the simplest and most direct method of network analysis. I have made a little assessment here of this method. It's not as relevant in practice as others, but the learning effect is really significant here. This is, as I talked about before in the previous slide, why it makes sense to still look at it. And the overview of the method, the direction of the currents in a network is assumed first, and then the relationship to each other between these currents is described using Kirchhoff's equations and also Ohm's law. This is the toolkit which we need to do this, to perform this method. And once we have an equation system for each unknown current, we can solve the resulting systems of linear equations and then determine all the current and voltage drops in a network. So the toolkit is Kirchhoff's law, Ohm's law, and then solving linear equation systems. And this is basically the content of the branch current method. Let's look at an example circuit. This one here has been shown in other videos before. We have two voltage sources, U1 and U2. We have three resistors, and we are now looking for the current distribution in the network. We have three current flows because we have three branches here. Step one in the branch current method is selecting a node. And first we need to select, for example, the upper node and use it as a reference point for the unknown currents to be determined. So we are always referring to one node. And this node is chosen, at least in this example, to the right side of R1, the top side of R2, and the left side of R3. So we have the upper node selected as the first step. Then in the second step, we are going to determine the direction of currents. The currents we're looking for are I1, I2, and I3. At this point in time, we might not be sure about the direction in which these currents are flowing. We have the voltage sources here on the left and on the right, and this gives us some indication as to the direction of current, but it might not be obvious to us at this point in time if, for example, the voltage source here on the right, U2, is working as a source, or whether it's being charged by the voltage source on the left, which has a significantly higher voltage. So it could well be that I3 is flowing in the opposite direction, but this does not matter at this point in here. If you assume a current to be flowing into the wrong direction, then in the resulting solution of the linear equation system, this will simply have a negative sign, and you will know that even though you have assumed the current I3 to flow from right to left, that it's actually in reality flowing into the opposite direction. So no matter what, you can simply assume current directions as you wish in this second step. Then in the third step, we're going to apply Kirchhoff's first law, and this law states that the sum of the currents flowing in and out of a node must be equal to 0, and this means we can relate these three currents in a very simple and in one single equation. It's the one you can see here, I1 minus I2 plus I3 equals 0. So inflowing currents are counted positively and outflowing currents are given a negative sign, just as we have done so many times before. Then in the fourth step, we're going to draw in the voltage drops, which we assume using the reference arrow system, which we have talked about before. The producers in this network are depicted in green and the consumers are depicted in blue. And as we have assumed these currents here, we are then also assuming the voltage drop direction. For consumers, it's pointing into the same direction, the reference counting arrow. So R1 is pointing from left to right, R3 is pointing from right to left, and the consumers here, the sources, are pointing from the positive to the negative terminal. Then fifth step, we're going to apply Kirchhoff's second law, which means the loop equation, which we are going to set up now. And this law states that the sum of the voltages in a closed circuit, a mesh, we have talked about meshes before in a small video, meshes and branches and nodes. So if you're not sure what this means, you might want to check out this video. But here you can clearly see it, what's meant by the loop or the mesh in this network here. We have a loop on the right, and we're going to count the voltage drops in this network here. Minus U1 plus UR1 plus UR2 equals 0. That's this equation here. Then we are going to do the same for the right equation here, plus U1 minus UR2 minus UR3 equals 0. And then in the next step, we're going to use Ohm's law to introduce the unknowns we are looking for. We are looking for the current flows, our I1, I2, I3, and by substituting the voltage drops across the resistors by the product of resistance value and current flow, we can arrive at these equations here at the bottom. So we have now two equations for three unknowns, which is one too few to already solve this network here, but at least now we have set up the two equations and we have also entered the unknowns into the equations here. But luckily, in one of the previous steps, we have already set up this equation here. It's the junction rule we have applied to the top node. So we have now I1, I2, and I3 in this neat equation here. We have the loop rules applied and which provided us with these two equations here at the bottom. And now we can simply reshape these three equations to the form you can see here on the right, which is the standard form which you need them in order to solve a linear equation system. So we have I1 with a factor of 1 in front, we have I2 with a factor of -1 in front, and we have I3 with a factor of +1 in front, just as you can see them here. We are going to rearrange these equations here in the mesh rule equations here. I1 also R1 at the front, I2 has R2, and I3 is not present in this equation here. This is why we factor it in here with a 0 in front, so we can have it in the same standard form as before. And we bring minus U1 to the right side of the equation, which is why it stands here. We are going to do the same for the lower equation here, which gives us this form here. And this can then simply be entered into a linear equation solver. The factors you have are 1, R1, and 0 for the first unknown, -1 plus R2 for the second one, and +1 plus 0 and minus R3 for the third one. And the result vector for this linear equation system is 0 and U1 and minus U2. You can then do this by hand if you want, using the Gauss method or Kramer's rule, but you can also get some help from the internet or from your calculator and use, for example, matrixcalc.org to solve this system of linear equations here to very quickly arrive at the resulting unknowns. And this is what I have done. I have used this website and also this mask they are offering to enter the values here, as we are given the values of the components here in the task, 4 ohms for R1 and 2 ohms for R2 and so on. Also the voltages, we can simply enter them into the linear equation system. We can enter them into the matrix they provide, and then the system provides us with a solution here. X1 is 5, X2 is 4, X3 is -1, and these are the current flows we are looking for. I1 is 5 amps, I2 is 4 amps, just as I have predicted before. X3, which we assumed to flow from right to left, is -1, and this means in reality it's flowing in the opposite direction, which means the source U1 is charging the source U2, which you can see from the simulated arrow I1, which is the arrow for I3 with a property or with a value of 1 amp, which you can see here on the right. So I have simulated the network, and the network simulation has arrived at the same results as the linear equation solver, which we have used from using the branch current method. Now let's quickly summarize the main items from this video here. Firstly, the branch current method is based on the selection of a reference node at which a sum of currents according to Kirchhoff's rules is established. Then secondly, with the mesh rule and Ohm's law, we can set up further equations in which the unknowns occur. So if we have 3 unknowns, we need 3 equations which are linearly independent to produce this system of linear equations, which we can then solve using the standard methods available to arrive at the results we're looking for. So the branch current method helps us to understand the principles of Kirchhoff and linear systems of equations, but as I told you before, in practice, the computational effort you get from setting up all these equations, especially with larger networks, this renders this method here ineffective because it simply takes too long, especially if you perform it by hand. There are alternatives to this branch current method, which are the mesh current method and the nodal potential methods, which is what we're going to look at in the upcoming videos. That's all for this video here. I hope you enjoyed it. If you have any questions, drop me a comment down below and I will try to help you as best I can. And now I wish you a nice day. See you next time here on The Fearless Engineer.